Okay, so good morning everyone. So in the last class we discussed about the P-MOS transistor. We concluded some of the short channel effects first, right? Substrate leakage and gate leakage and all that. Then we discussed about the P-MOS transistor and the key conclusion, right, for P-MOS transistor is Kp prime, Kp prime, and then what is the other parameter? Lambda P prime, Vd sat P prime. No prime there. There's no prime here either, right? And Vt naught P and gamma P. These are the 5 parameters for the level 1 SPICE model. All are negative numbers. Okay, so we discussed in detail why each of these parameters should be a negative number. Some of them are just because of the convention. I am looking at IDS, okay, and remember we said that IDS was K prime W by L into V max into VGS minus VT minus V max by 2 into 1 plus lambda VDS. So we were looking at current flowing from drain to source, and because PMOS current flows from source to drain, which is in the same direction as that of the charge carriers, because it's now because of holes. Drift is because of holes and not because of electrons. IDS will be a negative number. It's just a sign convention, and therefore Kp prime has to be negative. Then Vd sat P, of course, because now the potential has to be from source to drain. Higher potential has to be from source to drain by definition, and only then current can flow from source to drain, because current always has to flow from higher potential to lower potential, no change in that. So therefore the voltages become negative because of that, right? Then the lambda P is again because VDS is the negative number, right, for the current to flow. Lambda also has to be negative, only then the magnitude of the current can increase, right? Then similarly the threshold voltage has to be a negative number, and even gamma P. For gamma P, remember we had to take care of the modulus sign. Mod of psi s minus psi, it will be minus 0.25 plus VSB kind of thing that we got. If you have to take care of that, and once you are done with that, you will conclude that gamma P also has to be a negative number. Okay, this is what we discussed with respect to PMOS devices, and of course all the plots will now sit in the third quadrant, because everything is going to be a negative number. Voltages are negative, currents are also negative, so all the plots will be in the third quadrant, right? And this is a topic I started last time, and there were a lot of questions. So let me go through this resistance thing once more, okay, so that there are no doubts. After the class I had a lot of questions, okay. So the idea is, okay, we have derived equations for the currents of the transistor. We know how the transistor behaves with various voltages and stuff like that. That's fine. But how are we going to use this transistor? Invariably, we are going to only use this transistor either to charge a capacitor or discharge a capacitor. This entire course is all about that. How fast you can charge the capacitor, how fast you can discharge a capacitor, right? This capacitance can be because of its own parasitic capacitance, like I will discuss today, or it can be because of a load capacitance, right? So I have a capacitance discharging. So if I have a logic inverter driving a load capacitance, right, this inverter is going to either charge this capacitor or discharge this capacitor, and the delay of the gate is determined by how fast this action can happen, okay. So I also told you that delay is defined as the time it takes for the input to go to 50%, right? From there till the time the output reaches 50%. Okay. So if this is my VDD by 2 and this also is VDD by 2, then the delay of the gate is defined exactly as this delay. Okay, this is the delay. And we want to estimate this. Okay. So the simplified picture is we have a capacitor CL and an NMOS is going to discharge it. We will see why an NMOS cannot charge the capacitor or a P-MOS cannot discharge a capacitor. We will look at it later. Okay, but for now let's just look at this picture. The capacitor is charged, Vc of 0 minus equals VDD. So this inverter is going to now discharge the capacitor through an NMOS transistor. Okay. So this voltage V0 is going to fall from VDD to VDD by 2 because of the delay definition. That's why VDD by 2 is a very sacrosanct number. I am not worried about taking it all the way to 0. Okay. Now we have to make some assumptions to simplify our analysis, otherwise it becomes very difficult. So if for example, if the input is going to rise slowly like this, then that delay becomes a little hard to handle, right? If it becomes a ramp function, then I have to see when the device turns on, when it goes into linear, saturation, all that. It's very painful to do that. So we have to make some approximations to get a first order number, and then we'll incorporate this input slew also later on. So the assumption we are going to make is the input rises instantaneously to VDD. Okay, 0 to VDD instantaneous. Okay. So if at 0 plus the gate is at VDD, my V out is also at VDD, right? At 0 plus, just after I turn it on, in what region of operation will my transistor be in? Saturation region or velocity saturation, right? Because VGS is equal to VDD, obviously VDS has to be greater than VGS minus VT. You are removing some quantity from there. Therefore, the transistor is in saturation region. Okay. So the currents look like this, ID, okay, and this is V0. So, right, this is my point where it is VDD, this is VDD, and somewhere here is VDD by 2. I am assuming VDD is large enough such that it's to the right, VDD by 2 is to the right of VD sat. Okay, so that I don't have to deal with a change in region of operation. Okay, so this is an assumption. So what is the equation of the current IDS? Let's say it's velocity saturated. It is Kn prime W by L into Vd sat n into V. What is VGS? VDD, right? VDD minus VTN minus Vd sat n by 2 into 1 plus lambda V0. Suppose this is a long channel device, then this would be in saturation, where this would just be Kn prime by 2 WL, VGS minus VT, VDD minus VT, the whole square. Okay. So let me not worry about all that. I will just write this as I0 into 1 plus lambda V0. Okay. Whether it is velocity saturated or not, or it is in saturation, I0 is independent of V0. That's the only thing I am worried about. Okay. So now just look at the picture. The V0 is coming down, it's being, the capacitor is discharging, right? V0 is just the voltage across the capacitor and the voltage is coming down. So if you look at the resistance, it now becomes a function of V0, okay. So last class somebody asked me, why don't you do a derivative out here? See, in analog, it's okay to do a derivative because you fix your bias somewhere here and then you will do some sort of a small signal analysis over that bias point. So in some sense, we have linearized this whole thing here. So when you do a Taylor series there, you got to take a derivative and then you expand it in terms of the input variables. So therefore you take derivatives there. But here I am actually discharging it from VDD to VDD by 2. It's such a large range, right? So I cannot do that small signal analysis of taking a derivative here. I have to find some other way of finding the resistance, average resistance now, which is a function of V0, right? So R of V0 is simply what? V0 by I0 into 1 plus lambda V0. Now I have a function f of x that is going from a to b. I want to find what's the average value. What do? You just integrate and divide by the x2 minus x1, right? That's all I'm doing here. So I'm saying that R equivalent is defined as V final minus V initial into V initial to V final of R of V0 dV0. That's what I'm defining as the average resistance. Okay, so this I will now write as minus VDD by 2 because VF is VDD by 2, VI is VDD, and so I'm going to write this as VDD to VDD by 2 into V0 by I0, right? That 1 by 1 plus lambda V0 I'm going to write as a Taylor series because lambda is very small, okay. I can expand this approximately as 1 minus lambda V0. Okay, maybe I should put an approximate here, dV0. Of course, now I0 is a constant, so I will just write into 2 by VDD into V0 into 1 minus lambda V0 dV0, right? So what did we get the answer here? You solve the integration and you just get what? 3 by 4 VDD by I0 minus 7 by 12 lambda into VDD squared by I0, right? This is what we got. Fine. So if it is going to have channel length modulation, then this is the only way you can do it because there is a variation of resistance all through because of that 1 plus lambda V0, right? So now the interesting thing is, if it's a long channel device, then lambda is equal to 0, okay. So implies R equivalent is 3 by 4 VDD by I0 if lambda equal to 0. Okay, so the point I was trying to make last time is, okay, we found an equivalent R, right? Why are we finding equivalent R? Because I can now treat this as an RC discharge and I can evaluate delays in terms of the time constant of that RC network. Okay, but if lambda equal to 0, then this is just like a constant current source discharging my capacitor. Why is it a constant current source? Because there is no dependence on V0. Now if lambda equal to 0, the current basically just becomes a IDS versus V0. This simply becomes a flat line and this is my region of operation from VDD to VDD by 2. okay. And of course now I don't even have to worry about VD sat because this will always be in this thing. No, you have to still worry about it. You have to make sure that the VT is above some number, below some number for it to be in saturation region all through. Okay, so assume VDD is high enough, there is no problem. So this is now like a constant current source discharging the capacitor. Okay, so we did the same calculation in method 2. So it's a constant current source discharging my capacitor. Method 1 is you had a thing like this, R equivalent into and CL. Now what is the time it is going to take to, and what is this? This current is I naught, by the way. If lambda equal to 0, this current is just I naught. What's the time it's going to take to discharge from VDD to VDD by 2? If it's a constant current source discharge, C delta V by I, right? So the time is C delta V by I naught, CL, right? CL into VDD by 2 divided by I naught. Here the R equivalent was 3 by 4 VDD by I naught, which implies that the time constant of this RC network, right, let me call it tau prime, is R equivalent into C. Now the delay of this thing to come from VDD to VDD by 2 is 0.693 times the time constant. So this is 0.693 into 3 by 4 VDD by I naught, right. So this is approximately, again we'll get 0.51 or 52 or something like that. I naught into CL. Now these two answers indeed do match, right. Now obviously if lambda is 0, then the constant current source model is the right model because the transistor is a current source. Okay, so if you look at the model that we are using for delay, okay, this guy is, if you look at this V naught of t, it will start from VDD and then go linearly, right. What is this? C dV by dt equal to I, so I naught by C into t. Whereas this guy, if you see, V naught of t is VDD e power minus t by tau prime. So the two models actually follow different equations with respect to time, but this one is more accurate. Okay, so if you look at V naught of t versus t, you have a straight line like this for method 2. The method 1 is going to look like this. Asymptotically it will go down to this thing. So this is my delay tau and this is VDD by 2. So the two models give the same answer at that particular instant of time. Any other instant the two models are different, right? The delays are the same. Question, why do we even want to do it through the resistance method? One is, of course, if there is channel length modulation, then this current source thing fails. I have to now, if you can of course solve this from first principles by saying that I equal to minus C dV by dt and use the equation of the make I dependent on V and solve the differential equation, then it's fine. Otherwise I need to do it through this resistance method, which is a reasonable approximation because all I am worried about is the delay at when it comes to VDD. This is the only point of interest in this model for me. So if you ask me which is better, it really doesn't matter, right? And I also pointed out that beyond this, both the models are actually not valid. because when it drops below VDD by 2 and eventually goes below VD sat, the transistors goes into a linear region of operation, right? And there the equation itself changes. So when I do that resistance calculation, it will go into a different region of operation altogether. So that is not even worth sort of going through all the way down to 0 with that equation, because it's not of interest to us. Okay. So beyond this, invalid model. The reason I am pointing this out is you will see that we use certain models in this course which are valid only in certain regions of operation. Outside that region of operation, if you ask me what the value of the model is, I would say I don't care, because the model is not even meant to handle that region of operation. That's the point I am trying to drive home here. Okay. Any questions? So the other thing is, of course, later when I start putting transistors in series or in parallel, then it's very easy for me to reduce that network using series parallel resistance combinations if I know R equivalent. Current source model, I cannot do that. Okay. Any questions here? Okay, so let's look at this equation a little more closely. R equivalent is 3 by 4. I leave out this lambda parameter, I naught. Okay, if it is velocity saturated, then I naught is equal to Kn prime W by L Vd sat n into Vdd minus Vtn minus Vd sat n by 2. Okay, if it is a long channel device and it enters saturation region, then it is just Kn prime W by L into Vdd minus Vt whole squared and half. Right, this is saturation, velocity saturation. It doesn't matter. So this is a long device, this is a short channel device. Okay. So look at this equation of R equivalent now, right? Clearly it is going to be inversely proportional to W, 1 over W, because the I naught is sitting below, right? So therefore, if I double the width of a transistor, then the resistance of the transistor drops by a factor of 2, right? Or the resistance becomes 50% of what it was earlier. So this is one key technique that we will use. If you want to reduce your resistance, then you upsize the transistor, and that is what this equation is also telling us, right? Now what happens if VDD is very large? Suppose VDD is very large such that VDD minus VTN minus VD sat n by 2, right? Or VDD is very large compared to VT, then what will happen? Yeah? If it's velocity saturated and VDD is very large, what happens to the R equivalent as a function of VDD? Yeah? But there is also an inverse dependence on 1 by VDD minus VTN minus VD sat n, no? So if VDD is large, right? What does large mean? That is VDD minus VTN minus VD sat n by 2 is nearly VDD, right? This is just a first order thing to show you that R equivalent then is not a function of VDD. So if I have a 180 nanometer device and I operate it from 1.8 volt down to 1.5 volt, then the R equivalent will not change much there. Okay. On the other hand, if your VDD is very small, then of course these things cannot be neglected, and that has a more complicated relationship with VDD. In this course, we are going to deal only with higher VDDs. We are not going to bring down the VDD close to subthreshold or even low voltage operations. Okay. First, let me just go back to this picture of this MOS cap that I had. Okay, MOS capacitor, 2-terminal device that I had, metal, oxide, okay, and then I apply a VG and I apply a body, right? Let me call this gate. Now, as I sweep my VGS from a negative value to positive value, right, what do you think will happen to this capacitance of this device? Okay, I want to now do a CV plot. C versus VGS. If VGS is negative, then what happens? By the way, let me also put the thing. This is P-type substrate. VGS is negative. What region of operation is this in? Accumulation, right? So that means you will have a lot of holes sitting here. Right? Now, if the concentration of holes is so high at the surface, any negative charge that you put here is effectively going to be terminated right at the surface. The electric field will terminate right at the surface because the concentration of holes at the surface is that much higher. So, of course, there will be depletion region and all that, which is negligible. All I am saying is it is negligible. So, if you look at this capacitance, this is going to be just that parallel plate capacitance, which is epsilon naught WL by Tox. Okay. So, of course, this is my L. W is into the plane. Right, and this is my Tox. So, C naught prime was Cox, or let me just call it C naught, Cox into W into L, correct? So, this capacitance will just look like this. Now, what do? I move this into the positive region, VGS. VGS is going to be greater than 0, and then which region will it start operating in? Depletion mode, right? So, if you look at this, I am now going to put positive charges here because VGS is greater than 0. This will start depleting my channel. These are immobile carriers again. In the depletion mode, obviously there is negligible surface charge, right? So, the electric field will actually start from the positive charge and terminate deep into the channel also, like this, you know. So, therefore, if you look at the capacitance in this depletion mode, it is going to be a capacitance of the oxide plus, not plus, in series with a depletion capacitance. Obviously, if you put two capacitances in series, then it sort of drops. It's C1 C2 by C1 plus C2, and therefore this capacitance will now drop. Okay. Now, at some point the surface charge density starts increasing again, and when you reach inversion mode, the surface charge density will be so high, right, that I have been able to terminate all the electric field almost at the surface. So, therefore, the capacitance will now simply go up back to this old value that we had. This is just a sweep of capacitance versus VGS. once it goes to the so what do you think it will be? Okay. Hmm. So okay, so maybe I'll discuss this offline with you, but typically the picture is a little naive here that I've shown you. When you do it, things will change in a sort of a gradual manner, right? In fact, if you look at this picture, capacitance may start dropping like this itself. It's not so abrupt as I have shown here, okay, but there will never be a discontinuity because nothing is abrupt in reality, okay. But anyway, so I just want to point out that there is this picture. Now, where are we going to operate this device? Our transistor in, and what capacitance should we worry about? Should we worry about this value? Should we worry about this value? Or should we worry about this value? So let us say that the device is in linear region of operation, transistor. Where is it on this picture? Right side, it has already got inverted. So really, if you look at the region of operation, we are worrying only about to the right of this region. Even in linear operation, what I don't want you to assume is linear region means it's in depletion mode. No. When it enters linear region, it has already, channel has got inverted. That's how we have exceeded threshold voltage, right? Of course, it may not be as strongly inverted as it would be in saturation. That is fine, but still the capacitance is effectively this capacitance that we are talking about. And of course, as you just saw in the earlier picture, when we discharge the capacitor from VDD to VDD by 2, we are only in saturation region. Forget about linear region at all. We are not even entering that region. So clearly, we are only worried about this capacitance here, which is equal to C aux into W into L. Okay. So with that, I can move into the picture of the capacitance for an NMOS transistor or a PMOS transistor actually. It's a 4-terminal device. It turns out there are capacitances all over, okay, from all these terminals. This is gate, drain, source, body. Without loss of generality, I am just saying one is drain, other is source. Okay, here I have a capacitance like this, CGD. I'll tell you the origin of all of these capacitance, CGS. Then there is CGB. Then there is, CDB and CSB. Okay. So now we first consider the regular device where the manufacturing was perfect, in the sense that if I have my oxide thickness here, then wherever this diffusion finishes, exactly there the gate will start. Okay, this in fact is manufactured in something known as a self-aligned process. You grow the silicon, make everything silicon dioxide, then put a mask and then harden one region and make the other soft. Then you etch out the soft regions. So because the gate oxide is itself acting as its mask, right? It is a self-aligned process, and typically I will get a nice diffusion region exactly like this. Wherever this diffusion finishes, exactly there the gate will start. Okay. So for the total gate capacitance, CG is basically just CGS plus CGD plus CGB. Okay. I am writing this as 3 components because when you now go into saturation region, right, suppose this is my source and this is the drain, VD, VG and this is VS, okay, and body is also grounded. When you go into saturation region, I told you that the channel will pinch off, which means there is more charge on the source side than the drain side. So there will be a uneven distribution of capacitance actually in this kind of region. So what I am saying is the total capacitance CG, which is a sum of CGS plus CGB plus CGD, right, is just C aux into W into L, sum of these. But if you look at the distribution across various regions, in cutoff for example, CGB will be whole of C naught and CGS and CGD will be 0. Okay, this is just a sort of a distribution model that people have done. It's more relevant for analog guys, not for digital. Okay, if you look at the saturation region, the CGS will be more, CGD will be less, and the CGB is just made 0. So all I am saying is this total capacitance, which I have called C naught, is being distributed across these 3 components. For digital purposes, it doesn't matter because we are looking at the sum of these 3 components always. For analog guys, you have to worry about these AC values also, and therefore you look at whether the source has more capacitance or drain has more capacitance and all that. Okay, this is the ideal picture. Now what do you do after manufacturing it? You form your diffusions, implant N plus, then you have to anneal this device. When you anneal this device, these regions, right, will expand thermally like this. This is not depletion region I am talking about. The atoms will actually move because I am heating them. I am taking this to like 800 degrees centigrade. You have to anneal it in order to make all this even out, to even out all the manufacturing defects. In that process, the N plus will now diffuse under the channel as well. So what will happen is there will be a small overlap capacitance that comes here. This distance is called L overlap. Okay, so previously if you look at it, my channel length was this. Now after this diffusion, because of annealing, my channel length has become only this much. Okay, so what is my overlap capacitance? C overlap is, it's just like a parallel plate capacitor again, it's this part of the gate. How much capacitance is that going to form? The area is L overlap into W, right? So this overlap will be C aux into W into L overlap, right? So the net gate capacitance is CG plus twice C overlap, one for the drain side, one for the source side. So this I can write as C aux into WL plus C aux into W into L overlap. Okay, again note, what we have done is we have written all of this as some technological constant parameters into the design parameter. What is our design parameter? W and L. for digital design, even L is not a parameter, right? Even that is fixed at the shortest length. So this is basically W into Cox into L plus Cox into L overlap. What is the conclusion? If you increase the width of the transistor, the gate capacitance goes up. Okay? Any questions here? Yeah. Yeah. So finally, when I tell you what is L, right, that is accounting for all this. When I say W by L, whatever L you substitute there actually accounts for all this. Okay, they may start, for example, at 20 nanometer and eventually it will come down to 14 nanometer or something like that. And in the actual model, if you look at the model file that has been given, they do further calculations to reduce this L. You say L is so much, but internally that L will be reduced, and then that L will be plugged into the model for the current equation. Okay, remember now there is also a depletion region of this N and P junction, so there it will further reduce. So all of that will happen. Okay, yeah. Oh, because I have one capacitor overlap on the drain side, one overlap on the source side. Where? Huh? Oh, sorry. This one. Yeah, this is 2. Yeah. 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 No, be careful. C naught or Cox. Cox is just epsilon by Tox. Epsilon naught by Tox. No, that's why I'm saying that I have called C naught. I'm calling that C naught. Ah. Correct. Yeah. Correct. No. That's what I'm saying. Be very careful here. This is not because, these two are not because of overlap. I am saying this is actually a combination of whether the transistor is in saturation mode or linear mode or cutoff mode. If the transistor is in cutoff mode, then this CGB is C naught. CGS and CGD are 0. If it is in linear mode, then it's like the charge distribution in the channel is uniform, right? So therefore, CGS and CGD are just C naught by 2 each. And the third condition, when it is in saturation, there is an uneven distribution where there is more charge on the source side rather than drain side. Therefore, that capacitance again changes. So that's why I said the first picture is even without considering overlap capacitance, I have to write the capacitance as a component of 3 things, right? Yeah, but for digital circuit purposes, just assume that is Cox into WL, all sum of all these. That is not overlap capacitance. Okay? Yeah. So it's between gate body, gate drain, gate source. So the actual picture, if you want, is if you're doing high frequency analysis, then the way the charge changes under the drain and the way the charge changes under the source will be different depending on where you're operating the transistor. Therefore, the capacitances will change. So it's not just all 3 of them. It's not just CGB. CGB is when you are in cutoff region, right? And it's mainly in accumulation mode or something. Then it is just between the body and this. That's all. Yeah. In the total gate capacitance, this L here, right? This L here, that is the reduced L. Yeah, that has to be the reduced L. Okay. So now the other two components, which are basically CDB and CSB. The origin of these capacitances are your PN junction diffusion the PN junction reverse bias capacitances. Okay, so if I have a PN junction like this, right? This is my P, this is N. I have a depletion region here, right? Then this, there's a total distance of WD. This will now form a capacitance, right? And give rise to a capacitance in that PN junction. Okay? If I reverse bias this further, what will happen to the depletion region? It will increase, right? If I increase my reverse bias, the depletion region will go up like this. So what will happen to the capacitance? Yeah, so what will happen to the capacitance? It will come down, right? So the key thing is that it is a function of the applied voltage also. Okay, so if this is my applied voltage V, then if V sort of is less than 0, it implies capacitance also decreases because depletion region goes farther and therefore it comes down. Okay.